Concerns? Okay. Alrighty then. Okay, so the bell work, if you think about it, what did he do? Think about what you did with the simulation about how they knew they were at all atoms. You go back to that simulation, there was one where you changed what kinds of stuff there was. What effect did it have? It didn't matter. In fact, somebody asked me about how he knew it was in all atoms, and that's how he knew it was in all atoms because he tried a bunch, and it was always the same bending. It was always the same ratio. It always bent exactly the same amount. So that's how he knew it was in everything. Okay, so Rutherford. Okay, so J.J. Thomson, he was doing his lab, and one of the people that was there when he was doing it was Ernest Rutherford. So Ernest Rutherford was one of Thomson's graduate students. So he probably did a lot of the experiments. Because that's what happens is the lead investigator designs the experiment, but then their graduate assistants carry it out. And undergraduates wash the dishes. No, not really. Undergraduates do some of the less intellectually challenging parts of it. Okay? So there's people at every level involved, but Rutherford was Thomson's assistant. So while he's doing those cathode ray experiments, Rutherford's right there. Rutherford graduates and gets his own laboratory. Okay? So, time frame, we said they give Thomson credit for the electron in 1897, even though it wasn't widely accepted till later. So now we're talking about just about 10 years later, 1910. So it was just after he opened up his new lab that Rutherford went there. And because he worked with Thomson, he thought the plum pudding model of the atom was correct because it explained everything they saw. Okay? Got that plum pudding model. Got a bunch of negative pieces stuck in some positive stuff. It explained why you could get the negative pieces to jump but not the positive because the positive was too big to jump. Okay? And that same piece had to be in every atom. His goal was he wanted to see how big they were. What size are atoms? Measure them. What's the diameter of an atom? Okay? He used a new tool that had just been discovered. Radioactivity. Now, nobody knew why radioactivity worked, but that didn't stop them from using it. And the part of radioactivity used is called alpha particles. Okay? And for us, the important part is that there's actually a couple things. One is that they're positively charged, so the electric field's going to affect them. But they were as heavy as atoms. Remember when we did the Thomson simulation, if you wanted an atom to turn, you had to turn the charge up 1,000 times because it was 1,000 times harder to turn an atom than it was to turn an electron. So even though they didn't know what alpha particles were, they could tell they were positive by which way they bent. And they could tell that they were heavy by how much they bent. That they bent like atoms bent, not like electrons bent. So they were positive and heavy. And he shot them at gold foil. So what happens when you shoot alpha particles is if you hit something thick, like a piece of paper, the alpha particles get stopped. But if you make it thinner, some of the alpha particles can go through, but some can't. So that meant that the alpha particles were interacting with the atoms in your stuff. And he wanted to make it as few atoms as possible, so he picked gold, because gold can be made just a few atoms thick. I think the number I looked up on this was that the gold he used was about 10 nanometers thick. Okay. So that you're only going to hit a few atoms at a time. Okay. So he's got a positive particle that he knows interacts with atoms because enough of them will stop it. Okay. But he doesn't want to interact with a lot. He wants to interact with just a few. And he needs a way to see those alpha particles because we can't see them. So if you think about the two videos we watched for the cathode ray tube, the first one we couldn't see the beam, it just spun the wheel. But in the second one we could see the beam because they put a piece of paper in there. That piece of paper had a fluorescent coating on it. And anytime a charge hits that fluorescent coating, it glows. So anytime an alpha particle hit that fluorescent coating, it would glow. So this is on page 103 in your book. This is me trying to draw it. Okay. So the key components. First, he's got a big lead block. The lead stops alpha particles completely. He drills a hole into it and sticks the uranium inside. Now the uranium is giving off alpha particles in every direction, but only the ones coming this way can come out. So he's found a way to aim his alpha particles. Okay, he's tried to aim his alpha particles at the gold foil. So he's got an alpha particle gun. It's not really a gun, but it shoots alpha particles. The eraser doesn't want to work. There we go. Okay. What he expected the alpha particles to go pretty much straight through. He expected them to turn just a little bit. Not very much. And the reason why he thought that was because the positive charges were spread out evenly. Think about Thomson's model. It's a big positive with little tiny negatives stuck in it. The positive is spread way out. And if they're spread out, they're not enough to stop alpha particles. Now, if you could concentrate them together, they would. And here's an example of what we mean by spread out versus concentrated. Think a piece of paper, 3 or 4 pieces of paper is going to stop a bullet. Probably not. But 3 or 4 pieces of papers saved Teddy Roosevelt's life. He was out campaigning, traveling on a train, and the train stopped and he would get off the back car and give a speech off the back of the car. Somebody came up and shot him in the chest. And he stopped for a while. Then he finished his speech, and then he went inside. And when he went inside, he pulled out what he had in his pocket was a copy of his speech that had been folded over a bunch of times. And the bullet had been slowed down enough by going through that paper. Now, the paper, if it had been spread out, would not have stopped it. But because the paper was all concentrated in one area, it was enough to stop that bullet and save Teddy Roosevelt's life. Okay? So, but positive charges are like the paper. They're spread out. They can't stop the alpha particles. He thinks that what stopped it is that there's a whole bunch of them that you're going through. And that's why they stop eventually. It's because you hit a few at the beginning, and And as you go through the solid material, you run into more and more positive charges, and that pushes your alpha particle till it stops. That's what he thought was happening. So what he expected was he expected to see just a spot right here and maybe a little bit wider, maybe a few spots a little bit wider. That's all he's looking for. Because the positive, the green stuff, was not enough to stop the alpha particle. Now, I'm drawing the alpha particle as a line. It really isn't a line. It's a particle that goes through. But I can't, I guess I could make the particle go through over and over again. It says the mass was evenly distributed and the charge was evenly distributed. So this sounds like a pretty silly experiment. You're shooting things that you don't think are going to change very much. But this is what his plan was. Okay? The beams are going to go through. And the interesting part happens right here, where it comes out of the last atom. Where it comes out of the last atom, down here there's some positive stuff. But up here there's not. So this positive particle is going to be pushed from below, and it's going to spread out just a little bit as it leaves the atom, because it's got more positive below it than above it. Whereas this one, the positive's here, there's no positive here, so it's going to go that way. So as the beams leave their last atom, they are going to spread out. Now, if the more curved the beams are, just like a light lens, the more curved the lens, the more it bends light. The more curved the atom, the more it bends light, the more it bends alpha particles. And he was good enough at math that he knew if he could figure out how much it spread, he could determine the size of the atom that would make it spread that much. Go back to his original goal. I want to figure out how big the atoms are, so if I measure this spread, I should be able to tell you how big the atom is. That's why he set the whole experiment up. I want to know how big they are. And if it spreads out more, they're big. If it spreads out less, they're small. So he ran his experiment. And what he got was this. Okay. Most of them went straight through. And a few turned a little like he expected them to. Even fewer spread more, and that surprised him. And then very few, 5 or 6 out of 1,000,000, bounced off. Oh, what? So, Rutherford had to explain how that alpha particle ended up back there. How did this happen? And the quote that everybody attributes to Rutherford at this point is, he said, when I saw the alpha particles that had bounced off the gold foil, I would not have been any more surprised if I had fired a 15-inch cannon at a piece of tissue paper and the shell bounced off. So he said that this alpha particle should go through that gold foil like a 15-inch cannon. That's one of those big guns on a Navy boat. Probably 2-ton, 3-ton shell. Bounced off a piece of tissue paper. And he wasn't just exaggerating. He had done the math. The math said it should go through as easily as a cannonball goes through a piece of tissue paper. But instead it bounced off. So, that is where I want to stop for right now. So, what I would like you to do now, if I can get my computer to go the right way. Okay. What I'd like you to do now, so how did Rutherford explain it? He had to explain a few things. One of the things he had to explain was why did almost all of the alpha particles go straight through? And the reason why is because they didn't hit anything. Okay? The reason why they went straight through was because they didn't hit anything. That's a pretty good explanation. But there had to be a positive piece in that atom to push it away, because the alpha particle is positive, so positive and positive repels. So he knew that the piece had to be positive, and he knew it had to be really small, because very few turned. And the ones that turned were the ones that got close enough. If they get close enough, they turn. So if you followed the paths of those particles, the ones that are way on the edges, they go straight through. If you get close, they turn a little bit if they're that far away, but if they go straight at it, they're going to get pushed back. So by the number that got pushed back, you could tell how big that nucleus was. Okay. So how big it is? Well, since most of the particles went through, it was mostly empty. Okay? And scientists have this ability to understate things. Well, instead of exaggerating, they do the exact opposite. So when they say it's mostly empty, let me give you a sense of scale. What do they mean by mostly empty? Well, a baseball field with nothing in it is empty. A baseball field with a softball or a bowling ball out at second base is mostly empty. Because that's the sense of scale. The nucleus would be about the size of a softball or a bowling ball in the middle of a baseball stadium. So when they say mostly empty, that's what they mean. 99.999% of it is empty. And then there's a little tiny piece. But those positive pieces had to be heavy. Otherwise, they couldn't push back against those alpha particles flying towards them. Because the alpha particles were as heavy as atoms. So if they pushed those heavy atoms backwards, they had to be heavier. If you threw a bowling ball at a ping pong ball, the bowling ball would not bounce off. Because the bowling ball is bigger than the ping pong ball. The fact that the alpha particles bounced off meant they were the ping pong ball, not the bowling ball. They were a little piece that bounced off. So the thing they hit was heavier than they were. Now, if you've got a small volume and a big mass, you have got a huge density. And once again, scientists understate things. So when they say huge density, this is what they mean. If you had a teaspoon of just nucleus, if you could get the nucleus all to stay together, it won't stay together because it's positively charged, but if you get that nucleus all to stay together in a teaspoon, that one teaspoon would weigh 20 million tons. That's what they mean by big density. That one teaspoon would weigh 20 million tons. And that's why Rutherford wouldn't have been more surprised if he'd fired a cannon at tissue paper and it bounced off. He thought the atom was like tissue paper. It turns out it's got this huge mass with a positive charge that if you get close enough, it's going to push you away. And that small, dense, positive area in the middle, we all know is the nucleus. So now we've named the second part of the atom that you'd learned before. Right? You learned electrons before. You learned nucleus before. Now, last year in biology, you used nucleus. Different thing completely. There's no DNA in this. Okay? There's no DNA in this nucleus. This nucleus is just heavy pieces. Sorry, wrong one. Okay, we don't have time to go into how those other pieces were found, so you're just going to have to take my word for it. The proton. They found that in that nucleus, there was a positively charged piece, and that was the proton. And the proton is 1,840 times heavier than an electron. You don't have to know the 1840. Just think it's about 2,000. So, to give you a sense of scale, that would be, if the proton weighed what a car did, the electron would be a bottle of water in the front seat. That's how different their weights are. So it's much heavier than an electron. The neutron. They called it neutron because it was neutral. It doesn't have a charge. But it's got the same mass as a proton. So it's 2,000 times heavier than the electron. And those pieces are in the nucleus. So if you think about it, the heavy pieces are all in the small spot, and the light piece fills up most of the space. So most of the volume is taken up by electrons, and the space, that's the space is taken by electrons. Most of the weight is in the middle of the nucleus, most of the mass. So the modern view of the atom. The atom is mostly empty. When you put a bowling ball in a baseball field, you have changed it from empty to mostly empty. There are two regions. The nucleus, we just in the center, and you see it flashing there. I was going to draw it to scale to show you how big it was. But if that atom were the size, if you had a picture of an atom, if that was said with a picture of a baseball field, would you be able to see a bowling ball? That's how small it would be. So I had to make the nucleus look big compared to what it really is, so that you could see it. That's where the protons and electrons are. And the area outside of that is only known as the electron cloud. And the electron cloud is a place where you have a chance of finding an electron. Okay. Now, you might think that electron cloud was a cloud of electrons, but it's not. And here's how you know it's not. Hydrogen only has one electron, but it has an electron cloud. That electron cloud says, where around that nucleus are you going to find that, where do you have a chance of finding that one electron? So electron cloud is about where you have a chance of finding electrons. Okay. So the first three subatomic particles we're learning are the electron, proton, and the neutron. Scientists are too lazy to write stuff out all the time. So instead of writing out the word electron, they will write a lowercase e with a negative for a superscript. It's lowercase because we don't want it to be an element. Elements always start with capital letters. And the negative tells us the charge. So knowing that's what they're going to do for electron, what do you think they're going to do for proton? You probably guessed right. P with a positive sign. What about neutron? Well, it's pretty obvious it has to be N. But how do you say no charge? Do you leave it off? Well, if you just write an N without a charge, it looks like the letter N. So they wanted to make sure that it said no charge, so they actually put a 0 above it as a superscript to say that it has no charge. Okay, and we say a positive negative charge, we mean a unit of charge. Just like elements come in units called atoms, smallest pieces, charge comes in whole units. You won't ever have half a negative, or half a positive, or 0.2 negative. Charge comes in individual units. And that means if you have an electron and a proton, they cancel each other out exactly, because it's exactly positive 1 and exactly negative 1. So they end up at exactly 0, which is where the neutron is, neutral. So positive and negative charges cancel each other out exactly. Now, relative mass means compared to each other. So what this is saying is, if the proton weighed 1, then the electron would weigh 1/1840th. And the neutron would weigh 1 because it weighs the same as the proton. I could have also done that if the electron was 1, the electron's 1, oops, sorry. If the electron's 1, then the proton would be 1840, and the neutron would be 1840. Relative just means pick one of them to be 1 and tell me how big the other ones would be. So electrons are little. If they're 1, there's a lot for protons. Or if the proton is little, or if the proton is 1, then you're going to have a fraction of 1 for an electron. A tiny fraction. So relative mass just means compared to each other. So I got 2 that are the same weight and 1 that's really light. And the actual mass, this is the one we figured out, that Millikan figured out. 9.11 times 10 to the negative 28th grams for the electron, and 1.67 times 10 to the minus 24th for the proton and the neutron. You see how these change by a factor of 4? That's 4 zeros. Okay. The proton and the neutron are much, much heavier. So I got just a couple things left to share with you. This is the best animation I've seen of what's going on. Okay. You got the alpha particles coming through. Most of them go straight through. If they get close, they bounce off, or they turn. So you have most of them hitting right here. Every once in a while, you'll get one up here. And rarely, you'll have one hit back here. Now, the reason why they're hitting so much is look how big those nucleuses are compared to real atoms. If they made those much tinier, you'd hit much less often. And you'd end up with a really dark spot. And so if you get these to scale, see how they're drawn way too big here? That if this is an atom, it's drawn way too big, just like it was in my picture. So if they get close to it, they bend. If they don't get near either of them, they just go straight through. So 99% of them did this. A few did this. Very few did that. Because very few would hit those little tiny nuclei. And the last thing I want to do is I want to tell you my favorite joke. This is my favorite joke. 3 subatomic particles walked into a bar. It's always better not sharing. 3 subatomic particles walked into a bar. The proton went up to the bartender and said, "Hey, I'll take a root beer." The bartender said, "Are you sure?" The proton said, "I'm positive." The neutron said, "Hey, I'd like a root beer too." The bartender said to him, "For you, no charge." The electron went, "Hey, I've been coming here for years. You have never given me a free root beer." The bartender said, "Hey, quit being so negative. Everyone knows you're a lightweight." And that's how you remember the charges and the sizes of protons, neutrons, and electrons. Okay? So that's the end of the experiments that we're going to talk about this chapter. To talk about where the big pieces are. The next chapter after this one, we'll talk about where those electrons really are. How do you build an electron cloud? Okay? But that's where we're at right now is I need you to understand these experiments and how they told us about the atom and think about it in the context of how science works. They saw something their model didn't explain. Rutherford saw things bouncing off that shouldn't have bounced off. He knew the model he helped develop and had explained everything before. He knew that model was wrong now and he had to come up with a new one. He didn't throw away the idea of atoms. He didn't throw away the idea of electrons because those still worked. He just needed to modify them. And that's how science works. Okay? Our theories get better and better over time when we find new things to explain. But with that, this is where I want to stop for the day. Okay? Anybody have any questions? Okay? So if you look in the module, you've got some homework out of the book. I actually copied the questions for you. I had some free time this morning, a couple of minutes. So the questions are actually in Canvas. You don't even have to flip to the book. Then on Monday, there's the makeup test. If you want to take the makeup test after second period on Monday, please send me an email so I can add you to my list. Okay? And you'll see another assignment practicing these experiments to see if we can make sure we know what we were supposed to learn from them. And then we'll start talking about the things you've done with atoms before, where you counted protons, neutrons, and electrons. That's the next thing that's coming. Okay? Anybody have any questions? Okay. So go ahead and start the homework. Who's that?
If we took the retake last week, do we have to take it again?
Nope. If you took the retake, if you joined the Zoom and took it with me, you don't have to take it again. If you weren't in the Zoom, you didn't get graded. Does that make sense?
Yeah.
Yeah. You understand the need for the Zoom part, right? I mean, I'm not being unreasonable. I don't want to write 1,000 tests, and I want to see the people who are sitting in front of me are actually answering questions. Okay? So that's the reason for it. If I don't have anything else, you guys can work on that. You can stay here and ask questions along the way if you want, or you can go. I'm not going to chain you to a Zoom. But either way, have a great weekend if I don't get a chance to tell you.